Hello, guys. Good morning.
Hello.
Can you guys hear me okay?
Yes.
Excellent. Excellent. I'll start in a minute. I'm just waiting for people to trickle in here. So how's everyone doing? Any questions so far? Any feedback, any comments?
One thing I found, of course, I was having busy weeks, tidying up a lot of things for my university these couple of weeks, but I don't know if I'm lazy to read a lot or I don't have enough experience to messing around with the data using pandas or other things. Sometimes I want to know what I want to do, but I don't know how. So I left most of the exercise. I really needed, can I call a friend this week?
Yeah. I want to show you guys something. Let me see if I can pull this up. Right. So I'm going to show you guys this email. Go bring this up here. Am I sharing my screen yet? No. Okay. One moment. So hopefully you guys can see my screen here. This is one of the really good newsletters. I recommend you guys sign up. So, all right, let me see. So let's kind of go through this quickly. And some of you told me busy week, couldn't get the assignments. That's understandable, guys, right? Again, I'm not here to make you guys feel bad or anything, right? We all understand we have commitments. Sometimes, you have project deadlines, family issues, kids, whatever, right? So, but having said this, we still need to sort of keep you guys moving, right? I mean, the reason we are doing this class instead of, giving you guys a bunch of videos is there's structure. Right? I mean, I'm sure, some of you probably enrolled in Coursera, some of the video classes. We watch a few videos and then we kind of trail off, right? That kind of fizzles out. So I want to kind of, keep going. So again, don't feel bad, right? Again, my only thing is please don't drop out. Stay as, do as much as you can to stick with the class, right? So yeah, so, and that's why, I call it sort of blended learning, right? Meaning, you are doing something on your research, but also we are meeting each week to kind of keep you pushing forward. So don't feel bad at all. So here's a tip I want to share with you guys. This is from, by the way, let me put this. This is something you guys definitely should sign up. How do we get there? Yeah. So let me put this link here for you guys in the chat window. So it's called The Batch, right? So this is a very good newsletter that comes from Andrew Ng. So Andrew Ng is the same person who did a lot of online video classes. And this is one of the really good newsletters you should get because he gives a lot of information. Anyhow, so one of the things I just noticed this week is he said, look, as programmers, you can read this, right? As programmers, we all Google around for answers, and then when we find something on a Stack Overflow, we just copy paste the answer and move on. Right? We all do this, right? There's no secret, and there's no shame in this either, right? However, and this is something I've been doing for a long time, and and then now he said this, and I thought, oh man, this is really good. Okay, so what I recommend is, let's say you're looking for an answer. Let's say you're saying, okay, how to do factorization in pandas, right? So you hit a blog or you see some code, rather than copy pasting this, what I recommend is you actually type it in. You can look at the solution. That's perfectly okay, right? Look at the solution, but actually type every character in. And then what I try to do is kind of, right? I sort of, sometimes I sort of look at the snippet once, then I sort of try to type in, kind of trying to remember, you know what I mean? Like, I don't just type like, looking at, looking at and typing. I just look at it once and I say, okay, let me start typing. Now I kind of get an idea, right? And if I'm stuck, I look at the solution. Because to me, my brain learns that way. Because if I just copy paste, I mean, to me, like, I really haven't picked up anything, you know what I mean? But when I type it, it really makes a difference. So try this out. Right? And especially, in a fast-paced class like this, we are learning at a very rapid pace, right? You need to kind of train your brain, because there are some things if you just copy paste, your brain just will not absorb. So try this tip, right? Just type it in. Even if you're just looking at it, just type it in. And as you kind of improve, right? Type it like, type it then, without looking. They kind of see, can you kind of mimic this, right? Can you kind of, right? Yeah. Anyway, so, and I'm glad Andrew also mentioned this as well. And also please, I highly recommend signing for the batch, right? Newsletter. It's a very, very good newsletter. Good, guys. So looking at the curriculum. So this week, sorry, last week I should say, we were looking at feature engineering, right? Very important feature. Again, we're not going to, I just gave you guys a few links to, kind of get you guys started. Feature engineering is a big topic. We're not going to spend too much time on this one, but I still want you guys to get some basic idea of feature engineering. Yeah. So any questions or comments on this one? I know Vasily had mentioned something like, spending time reading, right? So again, this is something I am also trying to shape, because when I want to give you guys a reading list, I don't want to give you guys like 10 links, right? I kind of want to maybe like give you like, it's essential reading. I want this to be like maximum 3, right? And then the other stuff, I'll put this in extra reading. So it's like, if you get time, sure, you can get to it. Otherwise, right? Extra, that's it. Because I am also trying to keep this as streamlined as possible. So you guys can give me feedback anytime. You can say, hey, I read this article really, between these two articles, maybe the first one is the one we should keep. The other is kind of a, that's nothing. So you can please, you can give me feedback, right? Catch me on Slack or shoot me an email. Because remember, I kind of want to make this as a good guide for you guys too. And Vasily, you're kind of, I think, kind of alluding to something like this, right? Sometimes, just reading can be a little too much. Is that right?
It wasn't so much the reading as I'm trying to find examples of methods I can use to resolve or to present something the way I like. And they're always having something a little bit different than what I have. A little bit. I'm trying some different ways, and I just said, oh no, I had enough. My head is burning now. I will leave it.
Yep.
The lack of experience for using these methods and these objects, sometimes is burning my brain.
Yeah. Yeah. So okay, that's a good point. And here's another thing, right? I mean, in Python, I told you guys, there's always more than one way of doing this, all right? So usually when I find some interesting code, I actually, keep a copy of that, right? So you can see here, right? Python snippets, right? You can see here, for example, how to read a new file. You know what I mean? Like, whenever I see something, I just say, okay, oh, that's interesting. I'll just, keep, copy this code. So this way you're kind of building up your own library, and I will highly recommend this, just like a little notebook, right? Just a little Word document or text document you keep when you're browsing around. And also when you guys are going to look at, so I'm going to, feature a couple of solutions today. When you guys look at solution, you say, oh, that's interesting, right? I didn't realize we could do that, right? I actually kind of, spread a couple of snippets, I wasn't aware that you could do this way, right? So, and after this class, I'll save that. Yeah. All right, guys. So again, like I said, please give me feedback, right? I don't want this to kind of say, this is not like a one way. Please give me feedback too. Yeah. Sorry. Yeah, Vasily, go ahead.
Look, what I was trying to do, for example, Okay, you got say a set of data. You can group them by say 1, 2, 3 features, whatever it is. Fair enough. What I wanted to say is, for every group, I want to create, say, box plots and show them all the box plots of all the groups in one, graph. I failed, dramatically. I didn't know what to do. I found the data, but I didn't know how to pass it, where and how to present it in a way, and I just had enough and I quit.
And so that's a great point. Like, for example, I think you're talking about this example. You're trying to do like a box plot per zip code, right? I think that's more right. So one thing you should look at is something called a grid, a grid graph, right? So, 1 second. All right. So there's one thing you can look at. It's something called grid graph, right? So what it'll do, it'll basically help you, do kind of what you're trying to do in like a grid. So if you do like a, if you do a search for matplot grid, right, subplots. Yeah. So I don't know if you have an example, right? So something like this. What you're doing is you're kind of stacking, right, a lot of graphs side by side, and you can do it programmatically, right? So yeah, so this is, I mean, now you're sort of getting a little bit more into, a little advanced territory, right? And that's okay. You can research this, and like I said, matplot is highly extensible, right? You can sort of start looking at how people are doing this. So again, don't worry. Like I said, this is not something everyone gets it like on the onset. Like I said, right? Things like this. Yeah. So that means that what you're doing is kind of, you're kind of looking at multiple graphs in a single grid. So it gives, in one snapshot, you see what's going on. So what you want is something called subplot, right? So do some reading. It'll take you some time to kind of get this working, right? Because the syntax is a little obscure. Grid graph, I should say subplots, right? Yeah. Okay. But yeah, there's no shortcut, right? You can look at little sample codes and then kind of start forming your own. If you ask me to write a subplot code right now, I couldn't do it. I have examples that I have saved, that I can sort of start with that. But if you ask me to write this like from scratch, I wouldn't be able to do it, right? Because the syntax and everything is kind of a little confusing, right? So and that's not the point, right? Because point is like there's something like this, and you know how to go do this. And the actual exact API, you can figure it out as you go along. And that's why, again, I always stress this. Once you have something that's working, save it, right? Because you don't want to keep starting from scratch every time. Yeah. All right, so hopefully I kind of talked a little bit about along this one. All right, so let me quickly review last week's material, guys. And so thank you. I have two people volunteered, so thank you guys so much. So it's Alan Lynn, thank you very much. So again, the code is actually open, right? So you can actually, right? You can actually look at the code. I'll post a solution here. Actually, okay, I'll share with you guys in a second. But for now, let's look at this here. This is the feature engineering to scaling, right? Or categorizing. Actually, let me start with the feature engineering one. This is Jenny and Yang. Thank you again, Jenny. So there are a few things I liked here, and I want to quickly highlight this. So this is feature engineering one, right? So I had you guys doing the reading. Basically, what is feature engineering? And basically kind of said, okay, let's start with the house sales data because that's something you're already familiar with, and start looking at what are the features that are important, right? So that's what I want to talk through this real quick. So reading the data, right? And we can start seeing, okay, which features might be important, right? For example, property type might be an important feature. But as we look at this, that's another thing I'm saying, okay, property type is actually a categorical data. We need to encode this before we can do machine learning, right? That's the next lab. So, and then, so when you do the box plot initially, the graph is not very good because why? We have a lot of outliers. And also when you do a describe, you can see right away, right? For example, sale price, you can see minimum sale price 3,000, right? Maximum sale price 11 million, right? There's a huge variations, right? So guys, the data sets and everything, again, if you know, everything is right here in your guide, right? So data sets right here, the links for data sets, and you can directly load from our cloud server. We host these. Okay, so you can do them from there, right? So, okay, root drive. This is the first time. Need some catch up. Let me pair you with somebody, and they can bring you up to date, right? So, so that's why I'm a big fan of Describe. And that's basically the only change I did was I kind of put a display option. So when it prints out the data, right, the sale price and everything, you see like a little commas and everything, right? It's a little bit more readable, right? That's it. Again, I can have this code saved. So every time I want to print some numbers, I can use this. And that's the only change I made for Jenny's notebook. All right, let me walk through this real quick. So anyway, so Describe tells me there are outliers, right? Box plot confirms it. I have like 0 bedrooms to 33 bedrooms, right? So at this point, I know there are outliers. So let's go about how do we remove them, right? So I asked you guys, okay, so I said, okay, how about we remove the top, 10, so do a trim 10%. What is the trimming 10%? We eliminate top 10, eliminate bottom 10, right? 10% of the data, and then and then do analyze on the middle data. So, and this is what Jenny is doing. So he's like, so she basically is doing 90% quantile, right, and 10% quantile. Perfect, right? So upper limit and lower limit, and then trim data is what? And here's a condition, right? House sale price less than upper limit and over lower limit. So you're kind of finding the middle ground, right? You have lower ceiling, lower limit, upper ceiling, upper limit, and you're finding the middle ground. Right? Now, this 10%, I chose it arbitrarily, right? There's no like a rule, right? You could just say, you know what, I'm going to do like 15% or 5%, whatever you guys want, right? And you can see how easy it is to do that, right? And then we look at the describe data on the trim data. And now let's go to the sale price, for example, right? So look at the minimum sale price. See, that's much more, right? 206,000 minimum. Maximum, 819,000, right? So we no longer have the extreme variation like 3,000 and 11 million that we used to have in the raw data. Remember, the raw data we had that, right? See, 3,000 minimum, 11 million maximum. And if you look at the standard deviation, it's like it's pretty large, 342,000. And if here standard deviation should be fairly small, right? Yeah, 136, right? So this is how you can sort of develop a sense on how to remove outliers. Again, this is just one point, just sale price, right? What if if you want to do bedrooms, for example, right? And I think she had one here. So by the way, now if you look at the graph, see, it's much nicer, right? So because why? Sort of the extreme outliers are removed, but we still have bedrooms here, right? So one thing you can do is, and so so you can sort of see here, Jenny's filtering using the bedrooms here, right? What you can do here, one thing I would maybe add this, like I would say, instead of that, I would sort of do so like things like, bedrooms. Looking at the bedroom, you can say, what, I want to consider bedrooms less than 6, less than equal 6, right? Because that gives me a reasonable, that gives me a large amount of data, in the meantime, avoiding all the extreme outliers. Again, guys, there's no right or wrong way of doing this. Again, if you ask me why am I choosing 6 bedrooms instead of 5 bedrooms, right? There's no answer. It's just like you have to pick a number and kind of work, dial up and down, right? So you can do that too, right? All right, so there's a zip code thing, right? So one of the things you guys will find is in the zip code column, and again, this is where describe is really great. We look at the zip code, look at the minimum value for zip code. It says -1. So here, it's kind of treating the zip code as a number. It's not really, right? But it's okay because we don't care about this at the moment. But this actually gives me an indication there's a -1 zip code here. That means an invalid zip code. So yeah, so you'll actually go and drop zip codes. You want a zip code to be positive, right? And ideally, you want a zip code to be 5 digits, right? I think zip code should be 5 digits, right? So anyway, you can do some as rigorous as you want. You can simply say just positive. Or you can say, 5 digits. And I remember last class, I think is it Vasilios, you actually even verify the zip codes, right? Compare this again the zip code database to say is it actual valid zip code, right? So yeah, so you can choose the degree of how you guys want to add this. Yeah. Okay. All right. I'm going to zip through this one real quick, guys. What else? Okay, so describe. Oh yeah, so another thing I really like in this one. So now that we have cleaned up data, all right? So what she did was she actually creating like a per bedroom stats, right? So look at this one, say group by bedrooms, right? And we are running aggregation. So you have to think like SQL a little bit, right? So group by bedrooms, you can do aggregate by, like, you know, for example, you know, what can you aggregate by? Mean, average sale price, right? Standard deviation, minimum, maximum. I think you can add median too, I think, right? That should work. All right, let's see. Oh, remember we talked about mean and median yesterday, so in the last session, because sometimes, especially when talking about, you know, house prices, median might be a better option because it, you know, it doesn't get influenced by outliers all that much. But now that we clean the data, you should see mean and median should be fairly close, right? There shouldn't be, you know, right? So see, there shouldn't be a big, huge difference. Anyway, that's good. So she's calculating standard deviation min max. It's pretty awesome, right? So now if you look at the pricing seems to be pretty much in line. Like, for example, you know, you can say one bedroom, you know, minimum pricing is 265 and the maximum is 681. Because remember, it's a per bedroom, right? So this is, again, we are doing one bedroom and per bedroom. There's another factor, which is basically zip code, because zip code is a big influencer, right? Because, for example, a 4-bedroom in one zip code might be twice as expensive in another zip code. And so here's, you know, another example of, you know, zip code wise, right? So she can ask, you know, looking at how many unique zip codes I have, right? These many zip codes. So then she picked one, right? And then she did like an average, right? So basically, you know, for in the zip code, what's the average price for, you know, 2-bedroom, 3-bedroom, 4 bedrooms, right? And then, you know, and then you can sort of expand on this. You know, you can say you can do this per zip code calculation, or you can even do things like, you know, mean, median, min, max. I mean, you can, right? You can actually start calculating as deep as you just want. Yeah. So zip code really adds another dimension. So eventually, what you're going to have to do is, like, you have to kind of, you know, if you think about this, you have to develop a report on a per zip code basis and a per bedroom. Like, you have to kind of do this calculation. Where was the, yeah, you have to kind of do this calculation on a per zip code level. So it kind of makes sense, guys, if you really want to get deep, right? Let's say you're a real estate analyst, you're trying to price houses. You kind of want to, you know, kind of know this on a per zip code level, right? And then you'll say, okay, a new house comes on the market in the zip code. You say, okay, it's a 4-bedroom. You can say, okay, you know, on average 4-bedrooms sell for, like, you know, around, like, you know, say, you know, 499 or 500,000, right? So, you know, you know how to price it. Yeah, that's it. So I will make the solution public, guys. Give me 1 second. Let me do it right now. It'll be easier. Actually, you guys, I don't. Sorry, let me do this. In the interest of saving time, I will make this public, right? I'll put this in your welcome guide, right? So, and you can see all of those. Okay, I don't want to spend too much time on this one. Good, guys. So that is outlier detection, right? That's pretty good work. Thank you so much, Jenny. It's a good work too. All right. Any question on this one, guys? Yep. Okay. So you get the solution files, and the other one is from Alan Lane, is basically encoding variables, right? So the idea here is when you get different variables, how do you encode them? So again, pitch engineering. So here's a couple of articles, right? And then I'm giving you some data points. Say, okay, here's like a very simple data frame. Looks like this. Just encode the status variable. So I'm asked to do like index encoding, or, you know, or integer encoding, meaning like we're simply going to assign a number, right? And also one-hot encoding. Okay, so let me look at the lens solution here. All right, so here's a data frame. Okay, so here's a, here's an encoding as category codes, right? You can also do another one. Basically, you can say, let me see if this works. You can say df status index equal, you can say pandas dot what's it called? Factorize. Okay, yeah, factorize. Okay, yeah, something like this. Yeah. So pandas has a factorize function, and what I'm factorizing df status. This should work. Let me see. Oops. All right, I need to take a look at what's going on here. Df status. All right, I will work on this one. I'll put the solution here. Oh, colors. Okay. Yeah. Okay. Right. So we can, and then it may generate different index, and that's fine. Right. Because remember, why? As long as each variable is mapped to a unique index, that's what we want. Right. So married to 0, single, as you can see, is 1. Right. Oh, that's fine. So again, don't worry if like mine and Alan's are not matching, but that's fine because these are two different encoding schemes. As long as we basically come up with a unique number, right? So that's it. So pd.factorize is an option as well. Okay. Also, now one-hot encoding, you can say basically get dummies, right? Again, pandas has all this built in. So take a look at this one, right? So we actually have a status category, right? And you can see, right, it's creating new variables, sorry, new columns. Status divorce, status married, status single. That's it, just one line of code, right? You simply say get dummies, right? These are the columns, right? And that's it. So, and at this point, there's no confusion, right? I mean, for example, here, I may be confused to say, okay, hey, maybe this is a regular number, right? It goes to the 0, 1, 2, 3. An algorithm might read this as, might try to read this as a regular number. But with one-hot encoding, there's no confusion because we know it's not a regular number, it's a vector, right? So, very good. And also Prosper data, right? So Prosper, has, I'm just giving you a simplified data, right? Prosper has a lot more columns, and you can sort of see here, right? Immediately you can say, okay, listing categories, right? Employment status, right? Income variable. So this is a binary variable, right? All of this you can encode, right? So that's it. So that was that. So any question on this one, guys? Again, you're going to get good at sort of looking at the data and say, okay, which one is encoding, which ones we can use straight away. Any questions on this one, guys? This lab?
Question here, for example, you do say category encoding or one-hot encoding. You have to keep somehow the references of what that means.
Yep. Mm-hmm.
Yeah, like when you're coming back to report on these things, zeros and ones don't really help.
Yeah, exactly. Great point. Actually, yeah, that is where. So when you do pandas factorize, right? So right. So here's the mapping. Let me do this. All right, and then. Right, so this is how they do, right? So when you do factorize column, they give you two things. They give you the actual data frame, right? Actual factorized variable, and also they give you the mapping. So the mapping is what you look at to do reverse index. Yep. Mm-hmm. Does that make sense? Yeah. So index, right? So index will look like this. So it's order, right? So married is 0, single is 1, divorce is 2, because they treat this like an array. So yeah, you want to save this because like when you want to do the final answer, you don't want to give them 1, 2, 3, right? You actually want to give them the original data, which is married, single, divorced. Exactly. So you should keep the mapping. Yeah. By the way, I don't know if you guys noticed this. Early on, right? I just did underscore, right? Like this. Oops. I did underscore. You guys remember this, right? The reason was because I didn't really care what this variable is. So that's why I didn't bother assigning a variable name to it. And this is very common in Python. For example, when a function returns multiple return values, right? For example, if you look at the factorize, you will see like what is returning, right? So it's returning a right actual array and the actual mapping. Right? And honestly, I know initially I didn't care about the mapping, so I said underscore. Anyway, so now if you need it, then you should assign it to a variable, and you can keep it around. Yeah, good. Good observation. Yeah, thank you, Vasilius. Yeah. All right, guys, any other questions? So this guidance here is basically, in our, right? So feature engineering, introduction, variable encoding, and scaling. All right. So and the final thing is scaling. This one I'll just quickly go through this one, guys. Again, so there are various ways of scaling data, right? So we talked about, and these articles can walk you through why we need scaling. The first one is pretty good. So it kind of tells you like various scaling formulas, right? Right? For example, min-max scaling, what is normalizing, right? It sort of shows you, right now, we are basically, by the way, when you think about normalizing, what do we talk? We talk about zero median, right? That's moving the data into a zero, right? Zero average. So your bell curve, excuse me, right? And also squishing the graph to a format, so the difference is like a 1 sigma. Anyway, you can read more about this. I mean, I know statisticians spend a lot of time obsessing about these values and the shape of the graph, right? But for us, we just want to simply understand, okay, what does it mean, right? When I say normalization, what does it mean? When I say standardization, what does it mean? Right? So take a look at the article, and it also gives you the formulas for different ways of scaling. So typically, we either do z-scoring or, right, or you can do min-max. Right? So learn these methods again. Like I said, you can spend a lot of time reading and researching these scaling data, but for our purpose, just the basics of scaling. That's all I'm looking for. Right? Now the exercise, same thing, right? I'm asking you to give you like a very simple exercise to look at, right? Look at the scale the number, so you can see there's a different scale, right? This is like in 2 digits. This is in 3 to 4 digits. So I'm asking to do different scaling, do standard scale, normalize, right? And also, kind of one of the real world data is like this NBS stats. I'm asking to look at the data, right? So let's see, right? Yeah, and here you'll see a lot of like for example, age, height, weight, salary. These are numbers that are in very, very different scales, right? So you probably want to scale. Yep, that's it. So again, so the idea here is, guys, and if you look at it, you'll see a pattern, right? The way I do this is the first exercise is basically give you very simple data, because we want you guys to understand the process. And then I sort of build up towards a real world data set, right? And there are a lot of real world data sets now. I just picked one that we've been using. That's it. Right? So that's what you kind of learn first, because usually when I start with the real world data set, people are gonna get confused by that, because the real world data set can be a little, can be not clean. There could be too much data. So we always start small, and then, right, and then build up to real world. Yes. Good, guys. Is that making sense? Any questions on this one, please?
No, just as a note here, as I understand also from the previous step, and here the scaling or normalization, we have to keep somehow the denormalization or unscaling process. So when we try to report somehow, then you, for example, you say you use Z values, yeah? Z values. Okay. You go and say this is the Z value, say, yeah, well, so what?
Good question. Okay, so very good.
Have to,
yeah, so you can
scale it, for example,
right,
unnormalize it somehow.
So here's how you will look at this, right? That's a great question. Let me explain this. I'm glad you asked this question. So here's the original data, right? So let me see, make it a little larger. I hope you guys can see the screen okay, because I have like a high-res screen. Let me make it a little larger so it makes sense to everybody. So you get the original data. Then what we are going to do is, right, we are going to actually scale this data, right? For our, could be a z-score, whatever, right? Some scale data. And then we are going to run then we are going to run machine learning algorithm on this data. So the ML algorithm is applied here, right? and then it's going to give you a result here. Right? Now, so when we do the results, right? The scale data is just the internal data for us temporarily. We don't make this public. So when we publish results, what we publish is this, right? We publish this guy, right? And also we publish this guy. That's it, right? We don't have to publish the scale because now this is a temporary data just for our machine learning model, right? We don't need to publish that. So when somebody sees it, they will see, okay, or for this input data, the result is this. They don't usually have to worry about, okay, well, what was the scale data and so on and so forth, because this is a temporary representation of the original data. Does that make sense? You can always go back. You can always do reverse scaling, but usually we don't have to do that because, like I said, most of the time people don't really care about the internals of the temporary representation. Yeah, good question. Yeah, so answer your question. You can go back, but most of the time we don't have to. Right? I can think of a case. I had to kind of publish the scale data. I mean, you have to publish the algorithm. You tell people what you're doing, so they understand. They can compare the nodes or whatever, right? When you're working with somebody. But for customers, input, output. That's it. Great question. Yeah. All right, guys. Anything else here? So it looks like you guys did pretty well, right? Again, please keep on, right? If you're a little late, if you're doing partial projects, please keep submitting them, right? Because it'll kind of keep you. My goal is to kind of keep you guys moving. Okay.
Suji.
Yeah.
Another stupid question because it was driving me.
Not at all. Go on. Yeah. Go on. Yeah.
In the plots, I really tried to expand them a little bit, either the y-axis or the x-axis, or to make somehow more readable if you have a lot of labels.
Yeah.
I failed.
Size of the plot?
Yes, the size of the plot or the scaling of the plot.
Yep.
I don't have enough experience and I just drive myself mad.
Yeah. So here's my thing to advise to you, right? Let me show you this. All right. So there are books written on Matplotlib, right? So why I say this is, when you have to write a book on a subject, that's complicated enough, right? So I always say, don't sort of, don't be hard on yourself because it's not straightforward. The thing about Matplot, and this is true for pretty much all the graph libraries, is you can get a basic graph with a couple of lines of code. But when you start customizing, then you sort of go into a rabbit hole, right? You can spend a lot of time customizing and shaping the graph, right? So, so the way I learn, and I mean, maybe I would say I maybe know about 20% of Matplot, right? And that's I've been able to get by with just that. So don't worry about you don't have to know like every in and out. So if you need to do this, okay, I can answer your question. So you asked subplot. The other one is called figure size, right? This you have to look at. And the other one is called X limit and Y limit, right? So you can do this, right? So do some Googling around, you'll find some sample code along this. Again, how did I figure this? Again, like you, right? I sort of started with a basic graph. Then you say, oh, I need to set the size of the graph. How do we do this, right? Google around, can I figure this out? Yeah. So if you ask me to write this from scratch, I cannot do it. So the way I will do is kind of the way I'm recommending this to you guys, this machine learning class being done is what I call, if you're familiar with tree navigation, right? Let me, actually, I may have this here, 1 second. Imagine you are trying to navigate a tree, right? Remember this is your computer science class? There are two ways of navigating a tree, right? One is depth first, meaning you start here, you sort of keep go all the way deep diving, right? That's one way, DFS, right? Depth first search. The other one is breadth first, BFS. So what you do is you traverse each level, 1, 2, right? You see the order, 1, 2, 3, 4, 5, 6, right? That's right. So the way I teach machine learning is basically this way. We start at the top, we learn as much as we want. So let's say, for example, you want to now deep dive on 2, then you go deeper. Because this way you can keep moving without getting stuck on one subject. Because if you sort of did the depth first, right, you can keep sort of burrowing into one topic and you may get stuck. And even at the end, you realize, oh man, I spent all this time, okay, for like very little gain, right? So always think about this graph, right? I mean, the way I'm teaching this class and the way I teach for software engineers is basically breadth first. Meaning we start at the top, we only go as deep as we need to. That also means you're going to have some holes in your knowledge, right? Kind of like, you're going to have, there are some concepts you may not understand right away. That's fine, because what will happen is, as you keep working, let's say you say, okay, why am I scaling? Why am I using Z scaling as opposed to min-max scaling, right? Maybe you don't know the answer right now, but as you're going to start working with the different models, you realize. So the way I sort of look at this is like a little Swiss cheese, right? You're going to start with like a bunch of holes in your knowledge, but as you work on it, the holes will get filled. So don't worry if you need this, and trust me, I mean, there are some machine learning concepts I'm not clear on. I don't know the answer, right? And that's fine. I'm not worried about this, because if I need to, I can go find the answer. So this is the system I sort of developed, and this is what I personally used, because I don't have a PhD in math or stats, right? I'm a software engineer. That's my background. So how do you learn machine learning effectively? So okay, so summarizing it, breadth first, right? We go deep as we need, and then also don't worry, you're going to have some holes in knowledge. That's just usual, right? And then if you need to know more, you can always go find out. So hopefully this works for you guys. And like I said, this is what I've been teaching for a lot of software engineers that companies like Walmart and Cisco and Intuit, and this has been pretty well liked, right? Because this way, I mean, we all short on time, right? We as software engineers, we want to get our thing is we want to get things working. So you just want to learn enough, but at the same time, the reason I'm sort of showing you guys some of the basics, right? For example, I had you guys doing some of the basic stats, right? Because we don't want to go in totally blind. And that's another approach I see. It's like, people say, here's a deep learning code, run this, and here you go, you don't leave on it. I've seen a lot of courses like this too. I don't like that either, because now we are completely like, oblivious to what's going on, right? I'm just clicking a button and then saying, oh, okay, I clicked this button, it took like, 30 minutes and, it gave me some results, right? So all I learned at the point is like clicking a button, right? Because I don't know anything else that's going on. So the reason I had you guys doing some of the prereqs is basically we understand some of the basics, not too much, right? Because we don't want to kind of start going too deep into, like, for example, feature engineering. And trust me, I could spend 2 weeks teaching this, right? But we don't have to, and we don't need to. Yeah. Anyway, good. So again, don't be too hard on yourself. Just kind of understand the process. We are going to go like top down, right? And if you need to know more, always do research. So like I said, I mean, you probably know, probably as much matplot as I do. so don't obsess about it too much, right? So good. All right, guys. So any final questions before we wrap up feature engineering? How are you guys finding the reading materials? Are they good? So another thing I wanted to ask you guys is, would you guys prefer videos or like like blogs kind of a thing? I don't know if you guys have a preference. So I sort of make it, if it's a video, I sort of make it a point as a video, because video is like, video is something you cannot skim through. You kind of watch the whole thing, right? I only feature videos that has like good animations and graphics, because that makes watching, right? Because I mean, I don't want to watch a video of somebody just speaking, right? I mean, what's the point? You just read. That's my preference. So you guys can let me know, please, right? If you guys find a good link, you can always submit a link. And this is something I really ask your help. If you guys find a good blog or a good video, please, let me know, right? Because I will add to this.
On this matter, I found some videos on YouTube about this feature engineering.
Mm-hmm.
trying to sit down and listen to it instead of reading, because as I said, my head was really overburning. But I found out also there was a link with their code, with the the Jupyter code.
Yep.
And somehow you just say, okay, I listen to you, I try to understand you, I can read the code and try to see how you do what you say.
Yep.
So I found it a little bit more I could say easygoing, because it is combining a few things.
Let me show you guys this page. Stated. Okay. Yeah. So there are some blogs I follow, and like for example, right? So this is this is one of the great blogs by J. Alamar. So he does what we call visualizing machine learning, right? And again, I'll put these links in our subject. So what he does, he spends a lot of time creating graphics and animations. Do I have animation here? Sequence. All right. Sorry, let me see if I can find this. I'm trying to find, oh, there we go, right? There we go. Yeah. So he kind of does a lot of things about, for example, here's kind of how a translation system works. So you feed one translation sentence, and how it translates the other end. So he creates a lot of animations, and to me these I really like those, right? And some of the videos too, right? People create animation. So those are my favorite videos, and I will share with them to you guys. So looking at your comments, I kind of get both options, videos and blogs. So I'll kind of do like a mix, right? My personal preference is I like to read blogs because I can quickly skim, right? I can say, okay, hey, okay, this subject I know, right? Because video I have to kind of listen to the whole thing. So to me, my time efficient thing, I can quickly look at the I like to sort of skim through very quickly, and I say, oh, okay, I want to spend some time looking at this one. Right. Anyway, I will respect your wishes. I will do a mix of videos and blogs. Right? Yeah. So good. All right, guys. We got to move on. Any other? Definitely. Yep. So. Yeah. So I see. You guys have preference of videos. And here's the thing, right? So for machine learning and deep learning, there are tons of content out there, right? And if you go to Google or YouTube, you do machine learning, usually thousands or millions of videos. My job for this, guided machine learning is give you guys sort of good pointers. So I'm kind of more like a curator, right? I'm kind of curating like good content, so you don't spend like too much time, waste a lot of time just just wandering around, right? So we kind of want you guys, keep you guys focused in the right direction. So maybe, if you say, hey, I watched, and maybe, you have a different video that's a better one, give it to me, right? If that's good, I will put this on the list. Yeah, absolutely. Yeah. So, all right, guys. So again, right, because you guys are doing a lot of work here, right? Because I'm only spending an hour with you guys, an hour or two, maybe each weekend, right? So bulk of the work, you guys are reading, you guys are doing the exercises. So you're doing all the work. My job here is kind of like a curator, content curator, right? So, and all of this content, these are really great content. That's why I don't bother recording videos, because there's no need to. There's so much good content out there. I just need to know where to look. Right? So, all right, guys. So, looking at the overall structure, right? We are done with feature engineering. Let me see any questions on the chat window real quick. Yep. So as you can see, as you read through the chat window, right? You will see, some people prefer blogs, some people prefer videos, right? So I'll also keep a mix of those, right? Because one of the things I like in videos, like for example, I like Jay's blog because it's very right. He creates actual visualizations. I know some of the videos I've seen, they are very good at visualization, right? So yeah, so I'll be mindful. I'll also try to do more. Good, guys. So anything else so far? So this week's, what we are going to look at, we are going to look at a little bit of machine learning. So now we are getting into machine learning, right? I want to give you a little overview, and also I want to show you a little bit of scikit, right? So you guys already have done a bit of a scikit, right? So here, I'm taking it a little deeper and then say, okay, just read a few chapters. We are not going to go look into the algorithm just yet. I want you guys to get the overall, right, overall idea. For example, you have scikit environment set up, right? You guys should know how to use built-in data sets, right? And how to generate some synthetic data. So all these things, these are some of the basic stuff. So again, I'm asking you guys to create like a little thing, right? So that is this week, the coming week. So for machine learning, right, there are a couple of, this is basically the basics of machine learning. I'm going to walk you guys through a quick setup as well. So let's see here, give me one sec. Let me send you guys the material. Give me one moment. Sorry. All right, guys. Here's what I'm going to do. It's going to take me some time. So what I'm going to do is I'm going to get started, and I'm going to give you guys the materials a little later. Okay. I don't want to spend too much time here. Okay. All right. Let me go through this one, and I will email you the slides as we go along. So let's talk about machine learning a little bit, right? Okay. So again, here's a video. Again, I'm not going to go through the video right here, guys, because you guys will watch the video on your own, right? So now that we know some of the basics, I want to talk about machine learning specifically. So what is machine learning? Machine learning is basically a computer learning to do things without being explicitly programmed. So we all developers here, right? You write code in C, Java, Python, what have you. So we write code. But can a computer learn to do things without being explicitly programmed, right? That's basically what machine learning is. So just to contrast to you guys, give you a kind of contrasting example, here's what we do right now, right? We actually write the rules, and when you apply the rules to the data, you get the answers. For example, let's say here's my rules for determining if this is the email is a spam. So like, I can say, if the email is from this IP address, this is spam, or if the email has, these spammy words, spam. So what I'm doing, I'm writing code, right, to categorize. But as you can imagine, as my data gets larger and larger, the number of rules I need to write, it just goes through the roof. So as a human, these are usually, it's not, we cannot cope with the amount of data, right? So that's where machine learning comes in. For machine learning, what we do is we don't write rules. We take an algorithm, we show the algorithm some sample data. So I say, okay, here's a bunch of spam emails. Here's a bunch of good emails. Now the algorithm actually learns from the sample data. Now I'm not telling what rules, what to look for, right? I'm not, all I'm doing here is I'm just showing the sample data, right? It's very important. And the algorithm automatically comes with the rules. And the algorithm has learned enough, then let's say, I'm showing a new email and say, what do you think this email is? The algorithm can determine spam or not spam. Does that make sense, guys, right? So this is how we look at, machine learning versus traditional programming, right? So the idea you want to compare is like in the traditional programming, we write the rules and combine the rules, right? We get, with the data, we get the answers. In machine learning, what we do is we actually show the data and the answers, and the machine learning algorithm comes up with the rules. Kind of flipped, right? So the whole concept is flipped. And you might ask me, okay, wait a second, if I know the answers, why do I need machine learning? Right? Now remember, these are answers to your past data. So let's say you're trying to do credit card fraud, for example. You already have some data that you already kind of maybe manually classified as, fraud and not fraud, right? So, and you're going to basically train the algorithm on the past data. So the algorithm will learn from this, right? It's going to, let's say this is fraud and not fraud, right? And this data you already have, maybe, you have, a team of analysts going through each credit card transaction and flagging them, whatnot, right? You have some data. And that's why you're saying you're giving the past data and answers to the algorithm, and the algorithm is now writing the rules. Now, why is this a good thing, right? Because as the data size goes up, as humans, for us humans are going to write rules, it just, it becomes exceedingly hard. But for machines, they just need more compute power, right? We just throw the compute power at this, and they can write like, maybe as a human, maybe I can write 1,000 rules. But a machine, a computer can maybe write 1,000,000 rules very easily, right? Because just compute power. So is that going to make sense, guys? Right? So how machine learning is changing software engineering, and this is where software engineers need to learn machine learning, because pretty soon, and this is already happening, right? What's going to happen is we are not going to be writing code like this anymore. We're going to be training models for for a lot of the tasks that we do right now, because the models will then create the rules. So our job becomes kind of training the models, right? And then in deploying the models. Is that going to make sense, right? So just like an evolution, right? I don't know if anybody has done like web programming, right? In the early days of web programming, you kind of had to do everything in a manual, right? For example, you had to submit, you had to write a form submission. You had to submit, you write code for user management. You had to submit, what if somebody requests a password reset? Everything we had to write, we had to write manually, right? But now, if you're writing in any modern web application platform, all these are actually done for you, right? They have like a plugin to manage user management plugin. So you simply import the plugin and bam, right? I get the whole user management functionalities in like one line of code. So what are we doing? We're kind of going up and up and up the stack, right? So same in machine learning. Machine learning, we're not going to be writing low-level code anymore. As a matter of fact, I think Facebook, they did a research. They have published a model that can write JavaScript code. So you simply tell the model, okay, hey, I need a JavaScript code to do a form submission, and maybe do like a something else with the form, and it'll actually write the code. How did it learn? Because it was trained on all the data and all the coding data Facebook has, right? And you bet they are like millions of lines of code. So yeah, right. So software engineering is evolving, and machine learning is going to be a big part of it. So that's why I insist always and say, every software engineer has to learn machine learning, because, right, some of the work we are doing right now is going to be replaced by algorithms soon. Right? Is that going to make sense, guys? Yeah. So. All right.
It comes to a strange question.
Go ahead.
We have the model trained, right? And imagine it is a model, as we said, about spam emails.
Yeah.
I use, say, my email, say, application, and sometimes tells me, do you think this is a spam, or this is an unsolicited, or this is what? This means this kind of new information, I have to go somewhere and probably incrementally train model. So now, what on earth is happening? Because do we really have to go through the whole training again, or can we do incremental training also?
Great question, right? So let me kind of rephrase kind of what you're asking, right? So imagine, let's say today I have, let's say 100 gigabytes of data, right? So we actually train the data on an algorithm, and that gives a model. So I have model version 1, model 1, right? So let's say, a month from now on, I have 110 gigabytes of data. Right? So now, now we have more data than we did, like say a month ago. So what do? A lot of the programs I see, we retrain the whole data, right? And you might see this seems like a waste, right? Because as I get more and more data, I'm sort of retraining the whole thing. Wouldn't it be better if I just take this model and just do like a delta, right? Just add this extra 10 gig, and that gave me like model 2. It is coming. I mean, this is coming. There are some models you can do. This is called incremental training, right? or delta training. So, you have an incremental model and you sort of keep fine tuning it, right? You can add a little bit more data and do this. So answer is yes, you can do this. However, not all the models support incremental training. Some models you have to kind of train the whole thing, right? So especially in deep learning, this is possible. What you can do is you can save a snapshot of the model and then just do like a delta training, right? Just kind of, so this is a delta and this is fine. A lot of the machine learning algorithm, majority of them are basically, you have to retrain the model because, they don't support incremental training. Yeah. So anyway, so good question. So it depends on the models and the methodology. So for the most part, I would say, around 80%. Again, just throw a number. You have to retrain the model. Yeah. Good question. Does that make sense? Yeah. So this is called incremental or delta training. Yeah. But we are making advances because as you get more and more data, right, this becomes more and more important because you imagine your data is going to keep growing, right? So your data is going to keep growing, right? And then over time, there's data and there's time, right? So if you need to retrain every time, your training time also keeps going to go up and up and up. So yeah, what we want is like we want some sort of delta training, right? So yeah, research is going on, but for now, a lot of the machine learning models are basically full retrain. Great question. All right. So guys, this slide deck, I'm going to send it to you guys. Let me see. If I have to generate the slide deck. Let me see if I can set slide 6. Give me one moment because this way you just want to look at the slides also. So let me see if we can send the slides to you guys. Okay, sorry. All right, guys. Well, okay, it doesn't generate, so I will send this out. Apologies, right? So I thought I had the slides ready, but I don't. But I'll send this to you guys right after the class. I wanna make some progress today. Okay. All right. So we understand the basic idea, right? Again, I'm not going to go through the entire slide deck. I'm just going to highlight a few things. So we understand the difference between machine learning and traditional programming. Right? So now, let me show you some data. Let's say it's the same house sales data you guys seen, right? Plenty of times. I have bedrooms, bathrooms, and size of the house, and sale price. This is past data. This data I already have, right? But what I want to do is I want to actually write a model to predict the sale price. Because remember, when a new house comes on the market, I don't know what to price it yet, right? Because right? So can I learn an algorithm? Can my algorithm learn from the past data? Remember, this is all past data, right? I have the data already, and this is the answer. Remember, you guys are asking me, how do I know the answer? This is the answer, right? Because this is what we are trying to predict. This is all the past data I have. So I'm going to come up with a formula: sale price equal some formula. I don't know what this formula is just yet, of bedrooms, bathrooms, and size. Does that make sense, guys? Right? So I want to learn this formula F from all the data. This is basically what we call training. Does that make sense? So let me walk you through a quick example. Here's I just have two variables, X and Y, right? X is the input, Y is the output. So this is the input, this is the output. Can you guys look at this data? So I want you guys to come up with the formula Y equals some X, right? What do you guys think the formula is? Can you guys tell me? So remember, this is your training data. This is your input, X is your input column, Y is your output column. What's the formula, guys? Can you type in the chat window? So Y equal something something. Very good, very good. Okay, so I'm getting a pretty good, okay, so you guys are saying X squared plus 1. So you're saying, okay, let me go through the answer real quick. Y equal X squared plus 1. Does it make sense? Yeah, so you can say, right, you can say Y equal X squared plus 1. But that's not the only formula, right? You guys also can mention something. You guys also mentioned 2X plus 1. Yeah, that's good. Also, you mentioned 3x minus 1. That's good, right? So perfect. So you guys, so you see what's happening, right? You guys are kind of looking at the data and coming up with a formula. Pretty good, very good, guys. So now I'm going to give you some extra data. Okay, right? So so again, this is the two, right? So I'm going to give you some extra data, right? You guys came up with, so these are the formulas you guys come up with. Y equal 2x plus 1, 3x minus 1, x squared plus 1. That's using the, you were just using just these two data, right? Now I'm giving you some extra data. So what formula is going to, what formula works right now, guys, with all the data? Yeah, it's 3x minus 1. So let's look at 2x plus 1, right? Will 2x plus 1 work here? No, right? It kind of fails on both. So this is out. How about 3x minus 1? It works for the first two rows, but then it kind of fails. So that's out. So what's left? X squared plus 1. All right. So how did you guys come to this? Because why? Because remember, we sort of started with the, when the data set is small, I had a bunch of choices. As I give you guys more data, now you can narrow down what the formula is, right? And again, I'm sure there are tons of other formulas you can come up with, right? So what's the takeaway here is, right? So you can see how you're learning a formula from the data, right? There we go. So this is basically, this is the machine learning, right? I'm showing you some data, and you have to come up with a formula. Because once you finalize the formula, right? So let's say y equal x squared plus 1. Now, any amount of x, right? You guys can see, right? So now you guys already have, y, you figure out y equal formula is x squared plus 1, right? Now, any x I can see, you can predict y. So if I say x equal 100, what's the value for y? You say, sure, no problem, right? I have the formula right here. Plug it in, right? Y equal whatever, right? 101. Yeah. So this is essentially what machine learning is going to be, right? I'm going to show you some data. We are going to come up with a model or a formula from the past data, right? Right. So this is a simplified explanation of machine learning, but this is it, right? I mean, obviously, we are going to, our formulas are going to be much more complex in machine learning, right? But you guys get the basic idea, right? So because sometimes people get confused if, what do I mean by learning from data? This is it, right? You guys just did it, right? I show you some data with some answers, right? So what I showed you guys is, this is my data, X, this is the answer, and I ask you guys to come up with the formulas. And you guys just did, right? And if you give more data, then, right, you come up with a more refined formula. Yeah. All right. Good. So good deal, guys. Right. So this is basically what machine learning is all about. Okay. All right. So I'm going to zip through some of these real quick, right. So a lot of the machine learning now, right? Again, so sorry, I mean, I'm just interested in time and sort of zipping through a lot of these things. Let's talk about some of the hardware, right? Because this is something, you guys asked me, one of you asked me earlier. What kind of hardware we use for machine learning, right? So if you think about processing, we might think like CPUs, like an Intel CPU, AMD CPU, right? But however, a lot of the machine learning right now it happens in what we call GPUs. What I mean GPU, graphics cards, like things from NVIDIA. The reason is, if you look at the diagram, you see here, I'm showing you like a CPU on the left-hand side and GPU on the right-hand side, right? So the CPU cores, they have to support thousands of instructions, right? I mean, they are the one running your, Microsoft Word and Windows and Mac OS, right? So they have to support huge amount of instruction. So their size is pretty large. So you can only fit so many of them in a single core, in a single chip, I should say, right? So here, I have 8 cores on a single chip. But if you take the GPU chips, right? GPU chips are, they don't have to support this many instructions. They only maybe a few hundred instructions. Because they're not used to like running operating systems and whatnot, right? But what they are designed to do is they are designed to do very quick mathematical calculations. Because when you play a video game on your Xbox, what happens, right? It actually, the one that draws the pixels is a graphics card. So they are heavily optimized for very quick mathematical calculations. And also their size is pretty small because they're only supporting a limited number of operations, right? So what you can do is you can actually stuff a lot of these cores into a single chip, as you can see. The latest NVIDIA, I believe, has 4,000 cores. Can you imagine how much power a 4,000 core GPU card has, right? I mean, that's insane amount of compute power, right? So that's why GPUs are now, actually being used right now quite a bit for AI work because they are so much faster. So I have a machine here. So the machine I'm actually using the presentation right now is an Ubuntu machine. I have a GPU card. So to me, when I run things on GPU, I get 10x speed up, 10 times, not 10%, 10x, right? 10x the speed up. So anyway, so that's why GPUs are really good. So a lot of the people doing deep learning, they will actually have a GPU card, right? Let me show you a quick demo, right? This is so again, I'm not going to go through the entire video. So this one, I'm going to just show the video. All right, this is the one I want to show you guys. This is a pretty nice infographics, right? So this is a comparison between three compute platforms, right? Brain, CPU in the middle, and the GPU card. So you can see here, right? A GPU has gone through 100% of the data. So it consumed all the data. But the CPU is only about 10%. And the brain is about half that, right? So the reason I like this one is because the amount of compute power we have on GPUs is just astonishing, right? So I'm gonna stop here. Again, you can watch the video a little later. The links are in the slide, but just to kind of give you a sense, right? So GPUs are the preferred platforms for AI work right now. Yeah, so GPUs also have cache and they have high capacity memory, right? Like for example, the NVIDIA, Tesla. I mean, again, I don't want to go too much into this, but yeah, right. If you do a search for, I think the latest one is Tesla, right? V100, right? And then, yeah, so I'll go here. Right, I have a board. I don't know if you can see this diagram. Okay, let me. There you go. Yeah. So this is the board, right? So this is a GPU chip in the middle, and these are all memory banks, right? So what happens is if you load the data into the GPU memory banks, then everything is self-contained, and they can do. I mean, they have very fast interconnects. So they don't have to load data from a computer main memory. What you have to do is like you have to load the GPU cache or GPU memory, and then the computer is very fast because like between the memory bank and the GPU, they have very fast connection, right? So anyway, right? So you can sort of look at these things. I mean, because NVIDIA is the big player here. AMD is also trying to catch up. Anyway, right? You can sort of read all this, all the good stuff if you go to the website. Okay. Also, right? So again, there are a lot of videos I'm sort of I'm not skipping through. And another thing that's going on right now, guys, companies are also creating their own AI chips. So the Google version is called TPU, Tensor Processing Unit, right? And this is a custom chip built for AI workloads. Like for example, if you guys use Google Photos, like if you're uploading Google Photos, your photos are being processed by TPUs, right? So you can sort of see a single TPU can process 100 million photos, right? So, there's an arms race going on right now. Everybody's building their own chip. Like I know Google was the first one. Amazon is building it. Facebook is building it, right? Tesla is building their own chip for self-driving. So right, everybody's trying to build their own AI chip because because that they view this as their edge in AI. Yeah. So, question was how much does these cost? Right, these GPUs are they're not cheap. So you go to Amazon and then you go like let's say NVIDIA, right, 2080 or something, right? Right. So, right. So you can see, I mean, this one I have. I have a 2070. It's like about $500, $600, right? But they can actually go pretty high. Like there we go, right? There's a 2080. That's like $1,700 just for the card, right? Not the computer, just the card, right? So these can get pretty pricey. And I think somebody mentioned 3080. I think that's the latest one. Yeah, right. So what is 3080? Right? It'll be pretty pricey. You can see, right? Yeah. Do even that 3080? Anyway, yeah. So you can see, right? So these are not cheap, but people who do a lot of machine learning, I mean, deep learning work, they're happy to pay for this because it'll save so much compute time, right? So because what takes like 1 hour on a CPU, you can do it in like in 5 minutes in a GPU, right? So anyway, yeah. So you can spend some serious money on these guys. And again, so again, we have Google TPU. There's like a video I'm showing you guys. Okay, you can see this. All right. So let's talk about some of the AI vocabulary, right? Very quickly. So what we are doing right now, there's one thing called narrow intelligence, meaning AI designed for certain tasks. That's what we have done a lot of advancement lately, right? So this is like your self-driving cars, your smart speakers, right? All these guys. The general intelligence is basically what we say, like your robot butler, right? We are many years, even decades away from those, right? So your Terminator or your robot butler that can do your dishes and do your laundry, they are still far away, right? So good news, bad news, right? so yeah. So actually, I see a post from Vassily. Yeah, you can actually, right, buy these deep learning workstations. You can actually, like I said, you can spend a lot of money. All right, very quickly, let's talk about what's the difference between AI and machine learning and deep learning. And I really like this one. This is pretty cool. I thought I probably so basically people said if it's in Python, it's machine learning. If it's in PowerPoint, that's an AI. so I thought that was pretty funny. But there's a subtle difference. So the way I look at AI is like an umbrella term, right? Machine learning is basically sort of math stat-based models. That's the focus for this class, right? Deep learning is a very specific subset of machine learning that uses neural networks. Right? So just going to give an example, right? So for example, AI could be anything smart. Like for example, let's say you're doing your taxes, you upload your W-2 form. How they can pass the W-2 form automatically and figure out all the numbers. That's smart, right? Maybe somebody wrote some code or whatever, right? But it's still AI. Machine learning is something typical, like let's say you're trying to prevent credit card fraud. And deep learning is more like more advanced algorithms like self-driving cars. So the history is a lot of the hard problems that we were unable to solve using machine learning algorithms are now being solved using deep learning. Right? So for example, image recognition, right, is a classic example. Doing image recognition with the machine learning, we did some progress, but not as much, right? But with deep learning, we made tremendous progress. Same with natural language processing, like doing like translations and things like this. They were hard to do with machine learning, but deep learning networks can do them pretty comfortably. So you sort of see the difference, right? AI, machine learning, deep learning. Sometimes I use them very interchangeably, right? But just understand there's a difference, right? Yeah. Does that make sense, guys? Any questions on this one? Sort of the little vocabulary. Yep. So the reason I kind of want to walking just through this, like, you need to understand some of the basics, right? Some of the concepts. All right. So neural networks, even though we are not going to look at neural networks in this class, I want to show you guys a kind of, the basic idea behind this. Let me show you guys this animation we came up with. All right, let me walk you guys through this. So when you guys look at neural networks, you probably see people drawing circles, right? What are these circles? These circles are basically mathematical functions. That's it, no more, no less, right? So each circle is a mathematical function. Just like any function, they take inputs and they produce outputs. And the outputs, as you can see, they're then sent to the next level of mathematical functions, and they do the same, right? They do some number crunching, they produce some outputs, they send to the next layer, so on and so forth. But you can see these mathematical functions are ordered in a certain way, right? You can sort of say, by layer, right? And also by so this layer has maybe like seven neurons, they're called neurons. The next layer has 5, right? So on and so forth. So this whole thing is called network. So somebody designed this network with these mathematical functions to do a certain work. So what happens is, let's say I'm trying to classify pictures, right? Because that's one of the things neural networks can do really, really well. So what happens is, let's say I'm showing a picture of a cat. So the signal is kind of traveling through the network, and all the functions are kind of doing their work, producing the output, right? And then finally, it predicts it's a dog. But we know it's wrong. We're expecting a cat. So what we do is we send the feedback back, right? So the feedback, as you can see, travels backward through the network, right? So data goes forward, feedback goes backward. And when the feedback comes back, the functions kind of self-adjust. They can adjust their parameters, right? Based on the feedback we are giving, right? Then the process repeats again. I'm saying, okay, sure, okay, try again. Same thing, right? Picture goes through, and this time they predict rabbit. Slightly better, right? But still wrong. So we give them feedback, right? So again, when the feedback comes back, all the functions kind of self-adjust. Okay, try again, right? So, and finally it says cat. So now the functions are tweaked just the right way so they can predict this picture as a cat, right? So that's done. So now show the next picture and repeat, right? So what we do is we show thousands of pictures, right, to the networks to train themselves. So and the data, as you can see, data goes back and forth, until the networks are fine-tuned. Is that going to make sense? So there's no mystery like neural networks, right? Like these circles, just think like just functions, right? And they are parameters. And all we are doing is that when you show pictures and training them, they automatically adjust themselves. That's it, right? So there's no mystery. But this is a very different architecture than a machine learning algorithm. Machine learning algorithms have usually solid mathematical formulas. Neural networks are very different, right? So neural networks tend to be more complex. So that's why they can solve some of the difficult problems like image recognition, language translation, things like that. Is that going to make sense, guys, on a very high level, right? Right? Machine learning versus deep learning, right? All right. So next keyword we need to understand is training versus inference. So when I say training, what I mean by that is, right? Remember, we start with the data, and we pick an algorithm. We train the data, right? And then that gives us the model. And the training can be computationally very intensive, right? So this is why, for give you an example, right? So the Google Translate model they use right now, it trains on 2 billion words on about 100 GPUs for 1 week. I mean, right? I mean, that's how much training it takes, right? So, I mean, it's a kind of extreme example, I mean, to be sure, right? But these are very common. When you're building very complex models, this is the kind of, compute power you need. This is why, people are dropping, like Vasily said, thousands of dollars on GPU machines because, right? Because that's what it needs. So training part tends to be very, very intensive, right? So once your training is done, once your model is created, then you show a new data to the model and say, like for example, let's say, is this spam or not, right? Is this credit card fraud or not, right? That's called prediction. And that is very, very fast, right? Because it's almost like you're looking at a formula, right? You're plugging the numbers into a formula because training part is where you actually calculate the formula. And that was hard. Remember, we just did it just now, right? Once the formula is ready, we simply plug in the numbers and bam, right? We get the result right away. So is that going to make sense, guys? Training versus inference. Inference also sometimes called prediction, right? Same thing. Yeah. So question was, can a machine learning program use GPUs instead of CPUs on a limited capacity, right? So a lot of the so to use GPU, our library has support GPU programming. So right now, the one we are going to use, which is scikit. Let me see what the status is. Scikit GPU support, right? There's very early stages, right? So right? So right now Scikit is not supporting GPUs, right? So again, I mean, there are reasons for this, right? So if your library supports GPU, it'll automatically, use GPU when it's available. But for example, TensorFlow, the library for deep learning, they support GPU, right? Because remember, deep learning programs use enormous amount of compute power, so they have to support GPU, right? So the traditional machine learning algorithm, not all of them support GPU at the moment. Yeah. So, and also just to kind of give you a sense, right? I mean, not everyone needs like these high-end GPUs, just to be sure, right? A lot of the machine learning is done on a typical computers using CPUs, and we are just fine, right? So but at the same time, I kind of want to show you guys the sort of the state of the art, right? For example, when you're doing machine learning, deep learning programs, right? Just to give you some examples, you need a lot of compute power, right? So not even, you need like not just one GPU, but like many GPUs, right? Here they are using about 100 GPUs to train their language model, right? So, yeah. All right, guys. Another vocabulary, data size was a model size. Okay. So let's say I'm doing a facial recognition software, right? So I'm training my my model on a huge amounts of data. Let's say I'm just making really large examples. Like, let's say my data size is 100 terabytes. I'm training my model, and the whole training took 1 week. And at the end of the training, I get a model. My model is like 50 meg in size. That's pretty small, right, compared to the actual data size, isn't it? I started with like terabytes of data, and at the end, I just end up with like a model that's like a few hundred megabytes in size. So this is very typical. And let's say I want to deploy this face recognition algorithm onto my iPhone, right? So it's basically now our phones have hundreds of gigs of memory. So a 50 meg model is pretty tiny. We can deploy it easily, right? So, but I've seen state-of-the-art models that are like easily like several gigabytes, right? So those you probably won't work on your phone. So, but still, when you create models, the models you can train them on a large amounts of data, but the actual model is pretty small compared to the data. Does it make sense, guys? Yeah. So data size with model size, right? Very, very important to understand. Okay. Next one, algorithm versus model. So I've been sort of again using it interchangeably, but there's subtle difference. So algorithm is a generic formula. Remember the formula you guys just did, right? Y equal ax plus b. So here a and b are unknowns. I don't know what these are. So here, if I ask you, okay, x is 10, what's the value for y? I don't know, because I have these variables a and b I need to figure out. But what happens is, when you do the training, you take an algorithm, you train the algorithm, the training data, it gives you a model. And when the model comes out, these variables are figured out. Look at the color coding here, right? You can sort of see here, a is 3, b is 5. So now once you have a model, if I say x equal 10, what's the value for y? Sure, right? I just simply plug into the formula and then I get the value for y. So does it make sense? Because again, very subtly, even though we basically use some interchangeably algorithm model, but there's a subtle difference. So the formula is algorithm plus data equals model, right? Algorithm is generic state, okay? So having said this, kind of expanding on this, right? So let's say I took the same algorithm. Now I trained the algorithm with 2 different training sets. One is training data 1. So that's going to give me model 1, right? And this is the formula, y is 3x plus 5. I'm training the algorithm with another training data, and it gives me a model 2. That's a different formula, 2x plus 10. So I have 2 models now, right? Model 1 and model 2, they are different formulas. For example, so if I say x equal 10, you plug it in. So this model 1 says x, y equal 35, right? 3 times 10 plus y, 35. You plug x equal 10 here, this model is saying y equal 30. Now the question is, which one is correct? All right, so I start with the same algorithm, train on 2 different kinds of training data, get 2 models, which one's right? This we will look at as we look at algorithms later on. We will realize, right, how to pick the best model. Because for an certain algorithm, you could end up with different models. So which model, what's the best model? How do you pick that? Right? We'll look at this later on. Is that gonna make sense, guys? Kind of the basic algorithms, right? Yeah. Okay. Yeah. So kind of so again, the reason I'm doing this, sometimes people ask me, can I just show me the code? I could, right? Trust me, we are going to, you guys have been writing a lot of code, but context matters, big picture matters, right? So you kind of want to understand kind of where things are, right? So, all right, I want to do a couple more slides, maybe in another 10 minutes, if that's okay with you guys, all right? So let's talk about machine learning versus deep learning. Thank you, thank you. All right, so deep learning, we sort of shown you guys. I want to show you guys a very quick machine learning versus deep learning comparison, right? So what happens is, so here's a chart explaining machine learning versus deep learning. So one of the things that determines is data size. So if you look at the data size, here's the data size going to the right, and let's say the algorithm performance. Look at the machine learning algorithms. So they kind of, as you add more and more data, you train on more and more data, machine learning algorithm gets better and better and better. But after a certain point, they basically flatten out, right? Doesn't matter how much data you're going to add after that, they don't scale. But the deep learning algorithm, you can say they can start slow, right? But they kind of start increasing. Let's see if I can show you guys this. I'm running this program right now. Let's see. Right. No, mind. Actually, yeah. So I program is still running, so it's not ready yet. All right. So, so basically, this is how machine learning and deep learning are scaling with data, right? Deep learning kind of starts slow, right? So now, just to give you a little historical context, right? In the 80s and 90s, when we did this, we didn't have a lot of data. So a machine learning algorithm, right, gave us better results than deep learning algorithms. So that's why there was not a lot of research in deep learning in the 80s and 90s, because people said, hey, machine learning gives us better result. These deep learning networks or neural networks, they're not really performing. So there was not a lot of love for these guys in the early days, right? So you can sort of see what happens, right? So what's going to happen is this data is going to start moving to the right, right? Because we are, as time goes on, we are going to have more and more data. So kind of where we are kind of here, right? We have a lot of data. So neural networks can basically outperform pretty much any other algorithms. Why? Because they scale very well with data. So should we just abandon machine learning and just do deep learning then? Right? Right. I mean, if that's right, if that's a verdict. Right? So here's the thing, right? It's not as easy, because what if your data size is here? Because not everybody has data sizes like Facebook and Google, right? Most of us, we have modest data. So if that's the case, maybe a machine learning algorithm will give you a better result than a deep learning algorithm. You still see that, right? So I get this question all the time from my students, from our clients. Should we say, is machine learning obsolete? Should we just all switch to deep learning, right? In some cases, deep learning is can do real wonders. But in some cases, machine learning can outperform deep learning. So as practitioners, you need to kind of understand, okay, this is the problem I'm going to be solving. What algorithm do I need? Machine learning or deep learning? Is that going to make sense, guys, right? So I know deep learning is getting a lot of hype right now, and everybody's kind of chasing deep learning. But I mean, I'm a big fan of deep learning too. Don't get me wrong. But there are, as practitioners, you can say, okay, I'm going to step back and choose the best possible algorithm for my needs, right? Based on that. All right, guys. Hopefully this made sense. Yeah. All right. Next one is basically what we call, what kind of data do you have? And this is something I still ask my clients when they do machine learning. What kind of data do you? So first we ask them, how much data do you have, right? So so it'll give me a sense. If they say, I have like hundreds of gigabytes of images, right? Then that's one option. If they only say, we have a couple of gigs of some text data, that's another option, right? So what kind of data is important? Yes, I'm actually recording the session, guys. I will post the session in the link, right? So definitely. So if you need to leave a little early, that's fine. You can catch up on this one, on the session recording. So data size, when you look at data, we have two kinds, structured data and unstructured data. So let me give you a couple of examples, right? So structured data is basically, your data in your database. It has, columns, and each column we know the size and the type. Even CSV data, structured data, right? Because we know how many columns we have and what type and all that, right? JSON data, structured data, right? So unstructured data, things like your, photos, right? Images, Word documents, right? There's no structure, right? There's just a bunch of text. So do we understand structured and unstructured, right? So depending on what data you have, right, you may want to choose a different algorithm. So let me show you guys this, right? For example, design machine learning and deep learning, right? So this is not an easy decision. So for example, if you have structured data, we can try both machine learning and deep learning. Both can work, right? But if you got unstructured data, things like images, some audio files, things like this, probably deep learning will give you better results because the neural networks can adapt to unstructured data really well. So that's why a lot of the self-driving cars and all the computer vision algorithms are based on deep learning, right? Because why? Because they can process unstructured data pretty well, right? But also to get really good results, remember the curve, right? To get really good results, you need to have some decent amount of data, right? So, and one of the projects I was just part of a couple of months ago is like, as a client was training, wanted to do deep learning models, and they wanted to look at pictures of the production line, and to identify, like, for example, if a product comes out of the assembly line which is damaged, right? They want the algorithm to flag it, right? So, for example, if an iPhone is coming out on the conveyor belt, imagine the screen is cracked, right? So we want the models to identify this, and okay, right? So yeah, that's a reasonable. So we asked them how many pictures they have. They say we probably have about 50 pictures of bad products. Right? That's not enough, right? Because remember, these deep learning algorithms need thousands of pictures to learn from. So they can pick out like what's like a like a bad iPhone or cracked screen, things like this. So you need to have a lot of data to basically train these guys. Yeah. So hopefully machine learning, deep learning kind of made sense, guys. Any question on this one? Right. Again, look, I'll send the slide out to you guys in a few minutes. Yeah. So you want to understand, you guys have a pretty clear idea of what the landscape looks like. Yeah. All right, guys. So I think that's pretty much all what I want to cover. Sorry, I'll stop here. Yeah, go on. Sorry, was there a question?
Sorry. In mathematical terms, as I understand from what you say, we're both using polynomial, functions. So in the deep learning, I understand they use many more factors, polynomial factors. And in the machine learning, they a little bit, could say, less of prediction factors. So yes, it could be much faster and doesn't need so much size of data.
Right. Data, yep.
And on the other side, the deep learning really needs a lot of training.
Yeah,
exactly. For pruning.
Yep, exactly.
Autocorrelation, all this.
Right, exactly. So let me show you guys this. I'm looking for that one still running, right? Yeah, exactly. So, all right. I was trying to show you an example, but again, anyway, so my program's still running. So anyway, yeah. So deep learning models usually need more data and more training. Yeah. So, right. So again, the reason I kind of mentioned this is like, like I said, I always say, right, context matters, right? And also we need to kind of, before we go start writing code, we need to kind of understand where things fit in the big picture, right? So hopefully, you guys have a pretty good understanding of, what machine learning and deep learning is. I'll send the slide out, and then in the reading material, they will walk you through some of the, what kind of machine learnings, right? For example, what is the regression, right? What is the classification, right? So do some reading this week, guys. So this week I have two, right? Basic understanding of machine learning, and also kind of playing with scikit library. Okay? Those are the two things for this week, right? So this is a bit of a reading, right? Kind of so just so we understand the concepts. Yeah, question was deep learning and neural networks, same thing, pretty much, right? Yeah. So We use them interchangeably. Technically, if you're technically speaking, like when people say deep learning, right? So this is the architecture. Sorry, the technology they use is basically called neural network. So this little diagrams, that's a neural network. So the area of study is called deep learning, but for all practical purposes, deep learning and neural network, same thing. Yeah. So, right. Good, guys. So I'll stop here. And again, this video will be posted soon, so don't worry, it'll come up soon. Again, look at the exercises. I'll post the exercises too, and we'll keep going. All right, guys. Any other questions?
Good.
Good deal. All right, guys. So right now we are officially in machine learning. So I want to keep, keep moving forward. So please kind of, complete the exercises, the best you can. And I will see you guys next week. Yep. Thank you, guys. Thank you all. Yeah.
Very good. Thank you.